Get these assignment pages out because I'm amending today's assignment in your favor, so you want to pay attention. So make sure you're in the section 2-2 line. Everything's good up until you see the number 38. So get your eyeballs on 38. It should be 38 to 41, not 43. So however you want to change it, 38 to 41. Then the only thing in the next set that I want you to do is number 51. So I would scribble out 45 dash and the word odd.
Oh, wow.
Also, scratch out number 61.
Yes.
So this is the way the assignment should read. 1 through 17 odd, 18 to 23, 25 to 37 odd, 38 to 41, 51, 55, 57, 60, and 71. Got her? Okay. Those other ones deal with some stuff that I don't really feel is important for your learning. Okay. So section 2-2, it's called Power Functions with Modeling. And really what it should be called, in my opinion, is direct and inverse variation. Exposed to both, but probably not in the same class period and not in the same chapter. I'm going to remind you what they are. It's not hard, especially at your level of math. It's not a difficult thing. But you've got to be able to translate words into an equation that represents what you're reading. Okay? So, when you see the word, did I tell you guys about this before? Varies directly? No, I'm thinking algebra too. Okay. If you see the word varies directly, two things varies directly, and I'll show you some examples here in a minute. Varies directly, or if you see the words, because they mean exactly the same thing, it's just that different writers write it differently. Varies directly, or is proportional to. You see those words, then this is what you would write. For example, if the statement said y varies directly or is proportional to x, this is what you write. A is a constant. A different and very useful version of this is if you divide both sides by x, you get y over x is a constant. What that means is that if you had a whole bunch of xy points on this, every time you take the y value of that point and divide it by the x value, you always get the same number. That's an indication of varies directly. This is also what you're used to seeing as linear, as long as the line goes through the origin, because this is of the form y equals m, I think we called it m for slope, it's any constant, x plus b, except for the plus b is plus 0. So this is like any line that passes through the origin. Does that make sense? Where k is the slope. This is a different version of it that allows you to find k. So, before I go on to inverse variation, let me show you an actual example of this. If it says, for example, distance is directly proportional to time, or distance is proportional to time when you're traveling along a road, as long as the rate is constant. As long as you're traveling at a constant rate. Don't throw anything at that trash can again, because you obviously can't hit it. Don't throw anything again. You're a distraction, and I don't want you to be distracting here. If we're talking about moving along a road in a car, we'll say, and you're going at a constant 80 miles an hour, which is what I do most of the way to Boise, right? I mean, as long as nobody's interfering with you. And so if the rate is constant, then distance varies directly varies directly as time, the amount of time on the road. If you go faster, it takes less time. Still covers it. Well, that's not the issue. Never mind. That's not what I want to say. If that K is 80, that's your constant rate. This is distance equals rate times time. So distance is directly related to or directly proportional to time, as long as you're going the same speed. Okay? So it might say, once you figure out what K is, this time I just told you, you just have to be able to put it in the right place. Might say, okay, then find the distance when time is 4. So you say, okay, that's easy. What does that mean? You went 320 miles an hour, or 320 miles in 4 hours, right? Or it might say, how much time do you spend on the road to go 450 miles? So you use this same equation. You put 450 in for D. That's all for T by dividing. See? Well, it's not quite the same. Take 450 divided by that constant will tell you how much time it takes you to be on the road at that speed. You all knew that. That's easy stuff for you guys. But I'm just calling it a name. It's called directly related. Distance and time are directly related. If you spend more time on the road, you go farther. This goes up if this goes up. That's another thing about direct relationships. As one increases, makes the other one increase. So don't make too much out of this. Just watch for the words, varies directly or. And when you see that, whatever's on the front side of this equals K times whatever's on the back side. Okay? Is that right? Okay, I'll be doing some more examples in a minute. Now I want to put up here inversely proportional. And it doesn't have what's the word? Two things that have the same meaning. What are they? Synonyms. It doesn't have a synonym meaning. It doesn't have a synonym phrase. Only this one does. When you see inversely proportional to, or inversely related or proportional, either one. I guess it kind of does. Inversely proportional, inversely related. Either one of these words is inverse that's most important. Whatever comes here first, like to say, y is inversely proportional to x, it is y equals k over x. That makes good sense when you see the word inverse. You're going to divide this time. And a very, very useful form of this is that y times x is equal to k. What that means is if you're in an inversely proportional situation, it means that if you take any point on that curve and multiply the y value times the x value and get a number, any other point on that curve's y times its x will give you the same value. They're inversely proportional. I guess we could say, let's see. Distance. We could say time is inversely proportional to rate. If you said that, it would be this. Time is inversely proportional to the rate that you move. So, in this case, if we're still talking about rate times time equals distance, then this k right here is the distance you travel. If your distance is constant, like from my house to my mom's house in Boise, that's a constant 312 miles. Yes, I measured it. Okay. That would make this distance right here the same, and so you would have time is equal to 312 over r. Can you see that if I increased r, the rate that I'm moving would decrease my time on the road? Because it would make this divided by a larger number makes a smaller result. Besides that, you know that. If I go to Boise traveling 100, I'm going to get there faster than if I travel 80. So as this goes up, this goes down. That's an inverse relationship. You follow me? See? Okay. So this would lead to this. It would say, if I said y is inversely proportional to x, this is what you write. This is a different version of it. Two different versions. You just got to cross multiply. And this is a sample involving rate and time like we did with the other ones. Okay. There are many, many, many other relationships besides these things that are just linear. I mean, there's no power. We don't have any power on here. And look at the title of this section. And I have not even mentioned the word power yet. It's not hard. You just got to make a slight extension in what you see. Take a look at example 1. No, don't do that. Look at the table in the middle of page 188. Are you there? Table in the middle of page 188.
Right there.
You all understand that the symbol for pi is an irrational number, but it is a constant. Would you agree with that? Then based on what I've just told you, we can say in that first part of the table, by looking at the equation for circumference, 2 pi r, we can say that circumference is directly proportional to the radius because the constant is 2 pi. Kind of going backwards here. We're looking at an equation and stating what it is in English. It's one of those right there. K is 2 pi, so we say circumference varies directly with the radius. Or circumference is proportional to the radius because it looks like that function. You see what I'm saying or not?
Yeah.
Okay. Look at the next one. We would say area. Now we have to be careful how we say this. Watch this. Area is directly proportional to the square of the radius. Pi is your constant. So now we're getting the power stuff into it. It's not linear like it was. This was y varies directly as x. This says a varies directly as r squared. But they'll say it, the square of r. Area varies directly as the square of r, is what they'll say. Okay, the next one, this is the force of gravity. Notice we got a fraction involved. So we would say the force of gravity is inversely proportional to the square of the distance between the objects.
That was tricky.
Okay. It's inverse because k is on top, we got a fraction going, and it's f and d squared that are related. So the force is inversely related to the square of the distance. You see how I said that? Now that relates, okay. The next one is also inversely proportional. We say volume is inversely proportional to pressure. Straight up. Do you understand how that translates? You're gonna get a chance to do that. You're gonna give some formulas like this, and you're gonna have to write out the words in what that means, based on which one of these it looks like. Okay, look at example 1. Now we're gonna get a statement, we have to be able to translate it into an equation, but it's not gonna be as straightforward as these are. It could be like them though. Listen, from empirical evidence and the laws of physics, it has been found that the period of time t for the full swing of a pendulum, like this, hold it up, hold it back to your foot. When it returns to there, the amount of time it took to go over here and come back in a pendulum is related, that's what we're talking about. Full swing of a pendulum varies. If there's no word like inverse, it defaults to direct. It may not say direct, but it just says varies. That's a direct. Okay? Varies by itself is the default direct. So the pendulum varies as the square root of the pendulum's length, L. That's the length of the string. Let's translate that sentence. That's the most important part. The time that it takes, they're calling that capital T. Varies means varies directly. If you don't see the word direct or inverse, it means direct. That's the default. Varies directly, or just varies, as the square root of the length of the string. You see that direct translation of the words? Again, if you see just varies, this is the default. It could be just this. Instead of varies directly, it could just be varies. And that's also a direct relationship. Okay? Provided that the swing is small enough. You've seen people, if you take a pendulum and let it go way up here, and the string is flopping around. If it's a fairly small swing and the string stays tensioned properly, this is what it's on to if this is the case. Then it says, express this relationship as a power function. We did. Actually, to truly make it a power function, you actually have to have an exponent. That's not hard.
Oh.
See it? So when they say square root, the power is a half. And this is what they expect when they say express it as a power function. You got to have an exponent someplace, even if that exponent is 1. This one's a half. Okay. Would you look just before example 2? Just before that, we have a list of equations. We have x, not equations, just statements. X squared, x cubed, x to the negative 1, which is also 1 over x, and x to the 1/2, which is root x. You see those guys?
Yeah.
Those were all basic functions in chapter 1. Remember the 12 basic functions? Those were all mentioned. What we're going to do in example 2 is extend your list a little. This is not a basic function, but they're ones you're going to encounter a lot. It's okay. We're going to run into 2 others. And that's the cube root function, which is x to the 1/3. That wasn't mentioned. And 1 over x squared. We saw 1 over x, but not 1 over x squared. So we're going to take a look at these guys. And this is what we have to do with them. State the power and the constant of variation for each function, graph it, and analyze it. Remember your analysis? When you analyze something, you have to domain, range, continue, increasing or decreasing, symmetry, boundedness, local extrema, asymptotes, end behavior. All of those things are involved in an analysis. And if you forget what an analysis is, go back to this and listen for you right there. That's what I was reading. And I read the list that we learned to use for analysis. So here we go. A, we're gonna do it for A, and A is f of x equals, written as a power function. Written as a power function, it is, anyone?
X to the 1/3.
X to the 1/3. So I've got y equals x to the 1/3. The first thing we're supposed to do on this, once we get it written as a power function, it says state the power. It's easy. What is it? 1/3. And the constant variation, what's that? 1. 1. It's the number. The constant of variation is the number in front of this, and it's not written, so it's a 1. Do you understand that? No? We're comparing it to y equals kx. The power on this one, the direct variation right here is 1. The power on this is a half. The k on this is just k. The k on this is 1. That's it?
Yeah.
Okay, all right, that's first thing. And then it says graph it. I don't want to take time to graph it. It's the graph that you're seeing, the first one you see directly to the left. That is the cube root function. And analyze it. Now you look at that, and here we go. The analysis I'm going to run through really quick too. You see the domain is all reals. Can you see that the range, even though it seems fairly flat, continues to grow and is all reals? It is continuous, means you can draw it without picking up your pencil. It always increases. Always. If you're on that graph and moving to the right, you're always going up. Yes, you did. Is there any symmetry?
This origin.
Origin symmetry making it odd. Is it bounded?
No.
Has no floor or ceiling. Not bounded. Does it have any local extrema?
No.
No. Does it have any asymptotes?
No.
No. What's its end behavior? What happens as x goes really, really far to the right? What happens to y? It goes to positive infinity. If you go way far to the left, what happens to y? Negative infinity. Okay, let's go to the b part. Are we ready to move on? Okay, we have this function, g of x equals 1 over x squared. That's our function, g of x equals 1 over x squared. Can you write that as a power function?
X to the -2.
There you go, x to the -2. So the power is, and the constant is 1. And if you graph it, it's the second graph. It kind of behaves like 1 over x, except for everything happens in the first and second quadrant, because whenever you square something, you get a positive, no matter what. So all the graph is positive. So the analysis on this one after you graph it. Domain, everything but 0. You see it? It's asymptotic on the y-axis, so it's everything but 0. Range, only positive numbers, not even 0, just positive, from 0 to infinity. You see it? Okay. Is it continuous? This is tricky. This function is continuous on its domain, but discontinuous at 0. If you are only drawing, if you have your pencil drawing where the domain is defined, it will be continuous. Depends on whether you're on the right or the left. But if you are within the domain of this function, it is continuous. And yet it is discontinuous at 0. And the type of discontinuity is infinite. That's a very strange way to go left. That's what was in. When we ask about continuity, you have to qualify it. It's continuous on its domain, but discontinuous at 0. Is it symmetric? And if so, what kind? Y-axis symmetry making it? Good. Is it bounded?
Yes. Yes, on 0.
Yeah, exactly what you said. It's bounded below, and that's all. It's bounded below by 0. Never hits 0, never touches the floor, but it definitely has a floor. Okay? And are there any extrema?
No.
Nope. What's the end behavior? As x goes way, way right, what does f do? Goes to? Nope. As x goes way, way, way right, what does y do? Goes to 0. As it goes way left, it goes to? Doesn't mean it arrives. It means it's headed there. Okay? Okay, moving on. I know this is kind of boring for you. Hang in there. A monomial function. Monomial means one term. Mono means one. One term is what it means. A constant function is a monomial function. They're really boring too. This is an example of a constant function. F of x equals 4. That is a horizontal line of 4. That's all it does. But it is a monomial because it's made up of one term. Also, the more fun monomial functions are something like x to the n. Or k x to the n.
And that's still monomial?
Kind of looks like a direct relationship. What?
That would be a monomial still?
Yep, because it's only one term. There's no addition or subtraction signs around it.
Oh.
This is monomial, one term. One term. And they're a little bit more fun, a little more exciting to discuss. Take a look at the graph of several of them up to where n is 6. I'm talking about this corner of the book. Right here, right there. Okay, it's on page, the bottom of page 190, and I want you to notice the size of the window on this. The size of the window is in the first quadrant only from 0 to 1 in both cases. So we're looking really, really, really tight down near the origin. And notice that the smallest one, or the one that is the lowest, by the way, and this is really a true thing, I promise. When you're putting guy wires up, for example, or when you are somebody that's working for as a lineman and you're trying to string up new line or repair line, that swale in it, they honestly call that the belly. And x to the 6th has the biggest belly, most dramatic one. What's that? Well, it depends. We put up a weather tower out on the butte just above Idaho Falls, and I was thinking that we would stretch those cables really, really tight so that the guy wires came straight down like this and hold that thing right where we wanted it. But if you got on the end of one of those guy wires and looked up, it had a huge belly in it. Kite strings always have bellies in them because there's some weight to them that pulls them down a little bit. But it's impossible, as a matter of fact, in a physical way, it's impossible to have a line that has any weight to it at all. A chain, a rope, I don't care what strength, I don't care what it is. It is impossible to have be perfectly straight because you would have to put an infinite amount of tension on it, which would obviously bust it.
That's what
But all I'm saying is, I didn't want to get sidetracked there, but I did a little bit. I'm saying that when you graph those functions from y equals x down to y equals x to the 6th, in only from 0 to 1, when x is a fraction, x to the 6th has the biggest belly. It's the lowest one. But as soon as it crosses the 0.11, and if you were to look out into a window bigger than that, then x to the 6th quickly dominates and becomes the one that's going up the fastest, as you would imagine. But in that first quadrant, up to 1, it's reversed. Just something to note. Let's go to example 3. It says, describe how to obtain the graph of the given function from the graph of g of x equals x to the n. Okay, now this bit of attention, it is not hard, but in order to get this right on a test, you have to pay attention here. It's not hard at all. Do you remember when, if we were trying to describe the transformations of this, we would say f of x equals, let's say, -2 times x minus 4 squared plus 7. Do you remember how to describe the transformations of that? What would that be?
Up 7.
Up 7?
Right 4.
Right 4.
vertical stretch.
Vertical 2 and reflected over the x-axis. The one thing we didn't mention is, compared to what?
X squared.
Compared to the parent function, which is obviously going to be x squared. That's the reason why I've never asked you to mention it. However, all power functions are of this form right here. And if you change in, actually, these are parents, so I'm going to take that off. It's when this is 1. You can see from the graph that as soon as you change this, you got a different graph. So what I'm saying is here is if this is obviously squared, then the parent is x squared. But if it's x to the n, there are billions of parents in here. So when you state the transformations, you have to state this is a transformation of this parent graph. You have to include that in your statement. That's what I'm saying. Okay, so the first one, which is 2x to the 3rd, I realize that the 3 is obvious, but you still have to state what the parent is. 2x to the 3rd, we would say then that this is x to the 3rd vertically stretched by 2. It is the parent stretched by 2, and you have to identify the parent. That's all. That's the only difference between what you've been doing. You have to say it's a vertical stretch of what. And so on the next one, it would be, you would say, just look at it. Tell me what you would think in the B part of example 3. Describe that properly. What is it? X to the 4th.
Vertically shrunk.
Shrunk? Is it a shrink?
Yeah,
Shrink of?
2/3. And a reflection. Reflection over x.
Reflect over x. They go a little bit farther than this, but this is fine as long as I can tell what you're comparing it to. Listen to their words in the solution. We obtain the graph of f of x equals 2x cubed. All that verbiage is not required for me. By vertically stretching the graph of, they're identifying the parent, by a factor of 2. Then they make the statement, both are odd. They are. Oh, and that's one thing I forgot to tell you. So, when we're talking about monomial functions like this, if this is odd, the function is odd. If this is even, the function is even. But that is only for monomials. You start adding other terms back here, that may be all bets are off. But when it's just the leading term or just the power part of a deal with no other terms following, you can depend on this to tell you whether it's even or odd. So this one right here is x cubed vertically stretched by 2, and they're both odd functions. This is, and you could just say this is x to the 4th, identifying the parent, vertically stretched by this, reflected over the x-axis, and they're both even. Okay? You can see the graphs of them at the bottom. The dotted lines are the parent, the black lines are the daughter ones that we just transformed. And you can see the first 2 are odd, and the 2 graphs in the first picture are odd, and the 2 graphs in the next picture are also even. They're both even, one just as reflection. Not hard, right? Okay? Now, I want to do one more example for you, and then that's it. All the rest of this section is being cut out because that's what you lost in the changing of the assignment. What I would like you to do, just so that you have some experience with this, because there's one quirky, strange, bizarre thing that's going to happen. You need to experience it so you know how to deal with it. What I want you to do is I want you to go to example 6, bottom of page 195. And what I want you to do, first of all, so that you know where you're headed, go to your stat editor in your calculator. Before you start dumping all that stuff in there in your list 1 and list 2, I want you to do this. Are you ready? Go to stat, over to the calc menu, and go down and see if you can find what we've been talking about today. And tell me where it is.
Power regression, right?
Yeah, power regression. That's what we're talking about, is power functions. So when you go to do example 6 and it says fit a power model to this, that's where you're going to go. You do power regression, go to enter it, list 1, list 2, y1, see what happens. Okay? So please go to stat, edit now, and clear out your list and fill list 1 and list 2 with the data that you see in that table for example 6.
Wait, do we have to choose the power regression?
No.
Oh, okay.
No. So fill up list 1 and list 2 and then go tell them how it fits the curve. Make sure you get a window fitted for it so it'll all fit in there.
Jose Terrell, could you come to the office, please? Jose, come to the office.
And when you built your window and seen your points, go see if you can find a power regression.
I wish I was watching a lot.
No, you don't. You love being in there. You know it.
I know. It'll make me successful.
You know they go to certain numbers.
Yeah.
Are you all hitting a problem? When you go to I changed the domain for you? Oh. Are you all getting an error and you want to try to fit it? You got one? You got one?
Oh, I got an error.
You got the same error? I feel so dumb. You get the same error?
What'd you do?
I don't know. I crashed it.
Oh, yours didn't have an error?
Nope.
You can't read
I
it
redid
successful.
it because I swear the first time I was like, oh, I missed it. So I tried to.
Oh, what's your actually do?
What's your secret? Power right? You get this.
So are you all encountering an error as you go to do this with the power reg?
Camera did it.
She will.
Hey, wait a
Whoever did it,
minute.
how'd he do it? Make sure you're putting the right data in. We're not talking about the planetary data on the previous page. We're talking about the data in example 6. Oh, I did it wrong then. I did the one.
Oh, that's
That's how they look. Wait, we're not doing this one?
No, I did the one on the battery station ones, that's why.
Error domain, is that what you got? Error domain.
If you did the proper data over there, when you go to fit a power regression to it, you should have gotten an error. Page 195?
An error domain.
All right. The explanation I'm going to give you for this is not going to be very satisfying. But you'll have to trust me that I know what I'm talking about, and I know how these things are programmed, and I don't want to go into it with you. This is trying to fit it to a curve of this form. Y equals a b to the x. That's what it's trying to do. That's like k, and then the power function just like this. Like this, just different variables, right? If x is 0, then whatever this is, whatever that is, it doesn't know, it'll make it a 1. But the objective here is to find this. So your calculator really, really hates it when x is 0. It can't do it. It doesn't know what to do with it when x is 0 because it's not allowed to hunt for this when one of the points has x equals 0. Even though that may be an actual data point, it's very difficult for it to fix a power function because it's trying to find this and it says, well, I don't care what that is. That's going to be, I'm not doing that. It gives you a domain error. Domain means one of the x's that you gave me to work with, I can't work with it.
So you need to get rid of that.
So you need to, that's all you got to do. You got to go back to your stat, either that or observe it from the beginning. Go back to edit and just delete the 0, 0 point. You set your cursor on there and you use the delete button. We'll eliminate that, go to the next lot, the next list over, and eliminate the y that goes with it. So that you don't have your 0, 0 point, which is what the beginning of this was. Now try the power regression, and it will be accurate. Does not like to work with x equals 0 in this scenario.
All right, there we go.
Now if you hit graph, first of all, if your diagnostics are on, and they should be by now, you'll see this is a really great fit. It's really great. So now hit graph, and it should go through all the points really close.
My window's messed up.
And also, you need to build a window around the size of this. No, I really don't like it.
Yeah.
It does get to you, but you might want to say points too, like turn it plot on.
Okay.
Turn plot on 260 points.
What if it's still saying error?
Then that's your problem.
Mine says
I'd like to come in.
no.
Is that it?
Yes.
You can hit
Wait, mine are matching. I still have
Okay, that equation should be 4.03, we should truncate it, 4.03 x to the 0.5. So this is 4.3 root x, basically what it is, because that power on it was 0.49, it's close enough to 0.5 to call it.
no.
The equation we get out of this is y equals 4.03 root x, oh no, square root of b. Square root of, what did b turn out to be? X raised to b. Sorry. Oh, you know what? This is wrong. This is x to the b. I got that backwards. I was thinking exponential. I'm sorry. This is x to the b. So this would be root x here. Yeah, sorry. I just taught exponents in algebra 2 and that just flew out of my mind. I'm sorry. It's the other way around for a power function. Okay? So it ends up being 4.03 and then times x raised to the 0.5 basically. And this is x raised to the 0.5 written in radical form. This is what you get for your curve out of this one. Is everybody clear on that? I'm sorry, I screwed this up. This is a power function. This is an exponential function. They're really close. And I just taught this in Algebra 2 today, and that's the reason why I put that up there wrong. Sorry. B is a constant, and it's a power on x, and x is the variable. They reverse places, and they're two different kinds of functions. So, all right. So anyway, that's what the data tells you there, and that's it. Think you can handle this or not really? Should I really do this?
We're gonna find out.
Give it a try. See what you can do, and only do the exercises I told you to. Because if you try to do the others, it's gonna be rough. See you. Bye.